Thank you, and I would like to thank the organizer for inviting me to give this talk. So we talk about this joint work with Zdzis and Benedetta Ferrario, where we investigate some ergodic properties for the nonlinear stochastic damp Schrödinger equation on the full space, in the case in which we have a large dissipation. So I would like to start by briefly recalling the deterministic nonlinear Schrödinger equation and recalling some properties of this deterministic equation that we will need also to address the stochastic problem. So the nonlinear Schrödinger equation appears in many areas of physics, and it describes the propagation of waves where we have both a where we have a dispersive term, I Laplacian, and a nonlinear term, which is a power nonlinearity. So the solution is a complex valued solution, and we consider the case where U is defined on the full space, so we work on RG. And you see that in the equation, two parameters appear. So we have the power of the nonlinearity, which is sigma, and we assume sigma to be a positive real number, and we have a coefficient in front of the nonlinear term, alpha, so alpha can be positive or negative, and usually you suppose that alpha is equal to plus or minus 1. In the case in which alpha is equal to 1, you are in the so-called focusing case. Alpha equal to minus 1, you are in the defocusing case. So according to the sign of lambda, you have different behavior of the solutions, and you can understand the different behavior of the solution if you look, for instance, at the conserved quantities of the nonlinear Schrödinger equation. So we have that the nonlinear Schrödinger equation is an Hamiltonian system. You have the conservation of mass, which is the L2 norm squared of the solution, and you also have the conservation of energy, and you see in the form of the energy that you have first term, which is the kinetic part of the energy coming from I Laplacian, and then you have the potential part of the energy, and somehow the fact that you have conservation of mass and energy in the L2 space and H1 space tells you that these are the good spaces where you want to look for for the solution, and when we will deal with the stochastic case also for the support of the environment. So you see that you have to give sense to this term here that appears in the energy. So in particular, if you want that the energy is well defined for elements in H1, you have to require this Sobolev embedding here. And so both in the focusing and the focusing case, this tell you that basically these are the good range of parameters that you have to consider for the power of the nonlinearity. And if you again see at the form of the energy, you see the role played by alpha, which was the constant here in front of the nonlinear term, because you see that if you are in the defocusing case, so alpha is equal to minus 1, you have an energy which is always positive, and so basically it means that if you want to look for solution in H1, it is sufficient to work with the sum of the mass and the energy, because you have a positive quantity that controls the H1 norm. So in the defocusing case, usually the restriction that you consider on sigma are this restriction here that are the condition that guarantees that the energy is well defined in H1. When you are in the focusing case, alpha is equal to 1, so you have an energy that can be negative. So in principle, you cannot control the H1 norm if you just take the sum of the mass and the energy. So in this case, you have to introduce a modification of the energy, which is positive, and control the H1 norm. And when you introduce this modification, basically, you have to restrict your set of admissible powers. Okay, so this is the first property of the nonlinear Schrödinger equation, basically the fact that you have some conserved quantities, the mass and the energy. And from now on, I will denote by H the L2 space and by V the H1 space, which are the spaces where these quantities are well defined. The second important property of the nonlinear Schrödinger equation is the fact that it has a dispersive behavior. So in this case, we work on the full space, and when you work on the full space, you can consider the linear part of the equation, I Laplacian. It generates a group, and in terms of these groups, you can, let's say, see the behavior of the solution. So again, you have the conservation of mass, and here is the dispersive behavior of the equation. Basically, if you start from an initial datum, which is L1, then at time t, you end up living in L infinity. You have decayment in time, which is of polynomial. And from this dispersive estimates, you can prove the so-called Strickart estimates that are a crucial ingredient if you want to work with the nonlinear Schrödinger equation. So the Strickart estimates encodes the regularizing effect of the group associated to the linear part of the equation, and you see this regularizing effect, for instance, in the first estimate here. So basically, this estimate tells you that if you start with an initial datum which is L2 integrable in space, then you gain integrability in the sense that your solution will live in LP1 space where P1 is greater than 2 if you somehow take a mean in the LQ1 norm in time. So you have an increasing irregularity in the sense of integrability in space, and you can derive also a similar estimate for the nonlinear term, and the Qi, Pi, the exponent that appears here are the so-called Strickart pairs, so are couple of numbers that has to satisfy suitable condition, and I just want to emphasize that the condition the condition that they have to satisfy depends on the dimension where you live. Okay. So this is the second important properties of the nonlinear Schrödinger equation, and we will use also this property to address the stochastic case. So we are interested in studying a perturbation of the nonlinear Schrödinger equation in the sense that we add to equation a stochastic forced term, which is an additive noise. And the idea is that somehow this is an injection of energy in the system. So we want to compensate this term by adding also a dissipative term. So it's a weak dissipation in the sense that it's just a damping term, is a linear term, so it is not Laplacian, does not provide any regularization. And so the effect of these two terms is that you do not have conservation of mass and energy anymore, and you want to see if there is a balance so between these two effects. So you want to study, let's say, the statistical equilibrium, so the invariant measure of the system. We are interested in studying this problem here, so invariant measure of the nonlinear Schrödinger equation with a damping parameter and a stochastic. So what about the results in the literature? So here I quote some results. As far as concerned the existence of the invariant measure, there is a result by Kim of 2006 where he proves existence of at least one invariant measure on the full space, so on RD in any dimension, and he considered the defocusing case and the range of parameter, which is not the, let's say, the usual one for the defocusing case. And in 2017, Eken, Kukavica, and Sian extended the results by Kim, proving the existence of at least one invariant measure, both in the focusing and the focusing case in any dimension, with the usual assumption on the nonlinear term. Okay, and collaboration with Brze, Niak, and Ferrario, we study what happened on different geometries, and Benedetta will talk about it. As far as uniqueness, as far as I know, there is this result by the Bush-Dassault of 2005, where they consider the one-dimensional case on a bounded domain with the Dirichlet boundary condition, the focusing cubic case, and I prove uniqueness of the invariant measure and also polynomial mixing. So when you go to higher dimension, so the dimension 2 and higher dimension, you do not have uniqueness results for the invariant measure. So what we want to prove is somehow a result of uniqueness in dimension greater than 1. And so we consider this setting here. So we consider the equation that I mentioned, and we work on the full space on Rd when the dimension is equal to 2 or 3. And what are the assumptions on the noise? We consider a Gaussian noise. So W is a cylindrical linear process taking values in a Hilbert space U, and phi is a Hilbert-Schmidt operator from U into the V space. And we assume to consider zero-order dissipation, and lambda will quantify the magnitude of this dissipation here. And for what concerns the nonlinearity, we consider the usual assumption that you have in the focusing and the focusing. And we want to prove uniqueness of the invariant measure for this equation, and we are able to prove uniqueness of the invariant measure in the large damping regime. So at this stage, we are able to prove that uniqueness holds if lambda is sufficiently large. Okay. So, okay, what is the result and what is the idea of the proof? So, at first you have to be sure that there exists a unique solution of the solution, and this is a result by the Bois-de-Bouche. Once you have uniqueness, you can introduce, as usual, a semigroup associated to the solution process. So, Pt phi x is the expected value of phi evaluated in the solution process at time t starting from x, and phi is any Borel bounded function of t. Okay, so you can introduce this semigroup, and then you can formally introduce the concept of an invariant measure, so a measure mu supported on V such that it satisfies this relation here. And the paper by Eckentucarica and Ziane ensure us that you have existence of at least one invariant measure which is supported in V. So what we prove is the following result. So when we are in dimension 2 and 3, and we have to assume a stricter condition on sigma in the focusing case when d equal to 3, but I will come back to this assumption later on. If if lambda, which is the intensity of the dissipation coefficient, is bigger than a function that depends on the parameter of the equation, so in particular depends on the intensity of the noise and lambda itself, but we are able to prove that you have a decreasing dependence with respect to lambda itself. So if this condition holds true, then you have uniqueness of the invariant measure. So roughly speaking, this condition is telling you that the intensity of the dissipation term, lambda, has to be stronger than the intensity of the noise. So somehow it's a result that you expect, because you're saying that you are dissipating more than the energy injected in the system, and so this ensures you uniqueness of the invariant measure. So what is the idea of the proof? The proof relies on a reduction ad absurdum argument, and in particular in the proof we exploit the Birkhoff-Ergodic theorem. So if you have an ergodic invariant measure mu, then you know that for mu, almost every element in V, for any function which is integrable with respect to mu, then you have that when times goes to infinity, the limit of the mean in time converges to the mean in space, where you take the mean with respect to the invariant measure. So the idea is to use this ergodic invariant measure to prove uniqueness of the invariant measure, and of course in the proof we will need the suitable a priori estimates on the solution. So more in details, what is the idea? So we suppose that there are two different ergodic invariant measure mu I for I equal to 1 and 2, and we want to prove that these two ergodic invariant measure are equal. So this is enough, so it will be enough to prove this equality here. So if I consider a function in a suitable determining set, then it will be enough to prove that the integral of f with respect to the first invariant measure is equal to the integral of f with respect to the second invariant measure. And as a determining set, we consider all the continuous bounded function on V, which are Lipschitz, not with respect to the V norm, but with respect to the H norm. So it is actually enough to consider a less, a weaker norm. So we consider bounded function in V, but the Lipschitzianity is taken with respect to the H norm. And this is a determining set for the invariant measure. So we take two initial conditions that belongs to the supports of the two invariant measure, and we consider the solution processes starting from this initial condition, and I will call them UI. And so we want to prove that this equality holds true, so we consider the difference of these two integrals. Since f belongs to the determining set, so it is bounded, in particular it is integrable with respect to the invariant measure, so we can apply the Birkhoff-Ergodic theorem and write this difference here as the limit when time goes to infinity of the meaning time of the difference of the two solutions. And now we use the fact that f is Lipschitz with respect to the H norm. So you see that now it appears the difference of the two solutions in the H norm. And so this means that basically if we are able to prove this equality here, so when time goes to infinity, the difference of the two solutions in the H norm is equal to 0 pure more surely, then this is equal to 0, and we have the equality that we want to prove. So we have uniqueness of the invariant. So how to prove this limit here? You take just the difference of the two solutions, and by usual estimates on the nonlinearity and a Gromwell type argument, you end up having this estimate here. So you know that you can bound the difference of the two solutions at time t for any time with the difference of the two solutions at time 0, and then you have an exponential with this term here. So you see that you have something that depends on the damping term. So lambda is the intensity of the dissipation term. And then you have something that depends on the meaning time of the norm of the two solutions in the L infinity norm. Okay. So this term somehow resembles what you have in the Birkhoff-Ergodic theorem. And so the idea is the following. If we prove that when time goes to infinity, we can prove that this term that appears in the exponential is positive, okay, then everything will go to 0 when time goes to infinity, and we can actually prove the result. So we want to prove that when time goes to infinity, this inequality holds true, and so the idea is again to use the Birkhoff-Ergodic theorem, okay, because here we have a meaning time. And how can we apply, are we allowed to apply the Birkhoff-Ergodic theorem? So we prove that an invariant measure is supported in L infinity, and the L infinity norm to the power 2 sigma, which is what appears here, is integrable with respect to the invariant measure. Okay? So we prove that this integral is finite, and we actually prove that we can bound it in terms of a function that depends on the parameter of the equation, and in particular we have a nice dependence with respect to lambda because we have a decreasing dependence. So if this estimate holds true, then we can apply the Birkhoff-Ergodic theorem and says that this meaning time converges when time goes to infinity to this meaning space with respect to the invariant measure, but we know that this is bounded by a function that depends in particular on lambda, and it is decreasing on lambda. So if we impose that lambda is greater than this function here, basically we are able to prove this estimate here, and this will give us uniqueness of the invariant measure, and the condition to impose is this one. The dissipation parameter has to be sufficient. So the crucial estimates to prove is this one. So let's say all the technical part concern the proof of the fact that the invariant measure is supported in L infinity, and we have good bounds on this moment. So what is the idea of the proof? So in the proof, we use both the Hamiltonian structure of the equation. So we work with the energy functional and the mass functional, and we also use the dispersive behavior of the nonlinear Schrödinger equation. So we use the Strickart estimate. So the first thing to prove is that we have an estimate of this type. So the result by Ekren, Kukavica, and Tiane tells us that the invariant measure is supported in the energy space V, and we just need to derive some moment estimate of the V norm with respect to the invariant measure. And we have to be really careful because we have to check the dependence on the parameter lambda. In particular, we will prove that we have a bounce which is a function of lambda, but it is decreasing with respect to lambda. So the idea is, okay, to approximate the V norm to the power 2m with a sequence of bounded mapping, basically a cutoff sequence, approximation sequence. And so we know that since this approximation pk is bounded, then by the definition of the invariant measure, we have this equality here. And we know that PS of pk is nothing but the expected value of pk of the solution process evaluated at time s starting from x. And by the definition of pk, this is bounded exactly by the expected value of the solution process in the V norm. So we are reduced to obtain bounds of this term here. And what is the idea? In this case, you see that we want to have bounds in the V norm. And as I said at the beginning, okay, in the for the stochastic nonlinear Schrödinger equation, you do not have conservation of mass and energy, but you can use the mass and energy functional to control the V norm. So this is exactly the idea. So we derived some a priori estimates for the energy in the focusing case, modified energy in the focusing case, and using these bounds, we are able to prove an estimate for this quantity here. In particular, when time goes to infinity, basically we lost the dependence on the initial data, and we are able to have a bound for this quantity in terms of a function that depends on the parameter of the equation, and we see that the dependence with respect to lambda is good in the sense that we have a decreasing function with respect to then we somehow we can use the same bound also if we take the integral with respect to the invariant measure. And so we obtain this bound here for the approximating sequence, and since the sequence converges to the V norm to the power 2m, we derive the first bound. Okay, so just summarizing, the first bound that we need is proved using just the Hamiltonian structure of the equation, so just using a priori estimates for the energy and the mass. And we have just to be really careful in the estimates to keep tracks on the dependence. So the second step is to prove something more. So we want to prove that actually the solution belongs to a more regular space. So it is not only in V, but it is in a L infinity space, and we want to derive a similar bound for the L infinity norm instead of the V norm. The idea is similar as before. We introduce a suitable cutoff approximation sequence, And by a similar argument, you see that again, we start from the equality that holds for the invariant measure. So here the first equality is just due to the fact that here I do not have a dependence on time. Then here I use the definition of the invariant measure. And again, I can bound this term here with something that depends on the moment estimates of the solution process. So at this point, you see that we want to get some bounds of the L2 sigma in time norm, L infinity in space norm. So at this point, how can we prove this kind of regularity for the solution? The idea is now to use the dispersive character of the equation. So the idea at this point is to use the Strickart estimates. Because what is the idea? So we want to prove that we have bounds for the L infinity norm, and we can consider Sobolev spaces that are embedded in L infinity. So in dimension 2, we work with the space H1Q, where for a suitable Q greater than 2, and in dimension 3, we work with the Sobolev space H theta Q, where theta Q has to be greater than 3. And so we prove that our solution belongs to these spaces here, to these Sobolev spaces here. And the idea is, in fact, to use the Strickart estimates, because Strickart estimates tells us exactly this. I know that I start from a solution which is a L2 in space regularity, because the solution lives in H1. But with the Strickart estimates, I can actually prove that the solution lives to a more regular space, so a space of the form H1Q for Q greater than 2 in dimension 2, for instance. And I can choose a Q such that I have the Sobolev embedding L infinity. So using Strickart estimates, we are able to prove that the solution belongs to L infinity, and also to derive a bound for the solution in this norm here. And we see that this bound depends again on the parameter of the equation. In particular, we have again a decreasing dependence with respect to lambda, and it depends on the initial datum in the V norm. Okay. So using these estimates here, basically, if I go back, I know that this estimate that I want to prove is bounded is dominated by this term here. I have bounds for this term, and in particular, this bound depends on the initial datum in the V norm. So now I have to integrate this factor with respect to the invariant measure, but now I know that this is finite because I proved before that actually I have finite moments when I consider the V norm. Okay, so in this way I'm able to prove this estimate here, which was the crucial estimate in order to get the uniqueness of the invariant measure. And I emphasize that at this point that the condition on sigma that appears in dimension 3 it comes from this part of the proof, because what is the problem? The problem is that at this point you want to use Strickart estimates, so you have some condition on the Strickart pairs that depends on the dimension, but at the same time you want your solution to live in Sobolev spaces that are embedded in L infinity, and this also requires some condition that depends on the dimension. So if you put together all these conditions, then you see that when you are in dimension 3, you have a condition on the power of the nonlinearity that affects just the focusing case. And I just want to conclude by saying that this is the technical problem that you have also if you go in higher dimensions. So as I said before, our result holds in dimension 2 and 3, because in dimension 4, basically, if you combine the restriction that you have on the Strickart pairs that depends on the dimension, and the restriction that you have to impose in order for the Sobolev embedding to hold true, you see that you have a system of condition which is not compatible when the dimension is equal or greater than 4. So basically, this is the point where the proof fails to hold in higher dimension. And so I think I will conclude here. Thank you for your attention.